Thanks so much. Thanks for the intro. Thanks you for coming here. So I guess like I have one message that I wanted to say here today, and that's that the same technology that we're used to seeing to create all these beautiful pictures with V-Ray or Corona and all the other renderers, it actually has many other uses that go beyond just creating pictures. And I just want to talk about one of these other potential applications here, and that's in full color 3D printing. So before I start, I just wanted to give you a little bit of a background about what I've been up to over the last almost 20 years. So graduated in Prague from the Technical University, got my PhD in France, then I spent some time at Cornell with Todd over there. And then eventually in 2010 I returned to Prague and started this research group at Charles University in Prague. And since computer graphics is an applied field, so as an academic I've had lots of collaborations over the years, some with we could even say competitors of the company that I ended up eventually starting. So I actually contributed to Arnold a little bit. We have still an ongoing collaboration with Beta Digital and also with Pixar. And things have changed quite a lot in 2014 when myself and one of my students, Ondra, and myself and Adam, we started the company with the purpose of developing and commercializing Corona render. In 2017, we got together with Chaos Group, but throughout all these years, I still kept my position at Charles University because eventually I feel that I am really more of an academic than entrepreneur. And so all of this actually is kind of converging together into a research department that we're just building right now within the company in collaboration with the university, and that's something that we're calling Chaos Research. And I will talk about it a little bit more at the end of the talk. But now to the topic of the presentation. So I will start talking a little bit about realistic rendering, just a quick recap, and then I'll move to the 3D printing topic. So realistic rendering is everywhere. We use it for VFX, we use it for computer animation, but of course we all know here that it's also very important for architectural visualization, all sorts of product catalogs. IKEA is one of the prime companies that's actually quite open about using CG in their visuals. Started sometime in 2006, slowly, with just like sneaking one chair into the catalog. It worked out, no one noticed, so they just went on, and by now about 70% of the kitchen section of the catalog is actually rendered. Of course, cars, no one would actually shoot a real car today. It's all rendered. And what is this rendering? Okay, so when you look at it from an algorithmic point of view, the rendering is this process that gets a scene description. So we get some geometry, some materials, some lights, some camera, and then we keep crunching. That's the rendering process, and out comes a realistic image. And what I have actually put on this slide here is this word prediction. Because sometimes the image has really just the purpose of being a nice image, but sometimes the purpose might go a little beyond that, and that is especially in design processes where I would like to use a computer as a tool to tell me how my design is going to look like once I actually manufacture it. Okay, and this is going to be quite important for the 3D printing application that I would like to talk about here. And of course, we have plenty of renders, and they differ by their application, but they all share essentially the same core technology, which is the idea that we're trying to simulate very accurately on a physical basis the behavior of light as it bounces around in the scene. And this simulation actually involves trying to find all the possible paths along which the light can travel from the light sources all the way to the camera. So that's the basis here. And this is happening by just randomly picking these paths and just summing up their contributions, averaging their contributions. So we start with a noisy image, and as we add more and more of these paths, the image converges to some final solution. Of course, as we know, this takes a lot of time because the underlying so-called Monte Carlo process has not very good convergence properties, and well, that's why we have some jokes like that. Yes, rendering is a really slow process. So for that reason, there's been quite a lot of research into making this computation much faster. So all of these algorithms, they belong to the category that we could call, let's say, variance reduction. And you can indeed actually reduce the variance quite significantly. And actually much of my research over the last, let's say, 10 years was exactly in this direction. And some of these ideas are also implemented in Corona. This is another example from last year. So this is the direct illumination solver that we're using in Corona. Again, one idea for how variance can be reduced in rendering. So I will go into a little more detail in one particular idea that I worked on with Eugene Dion when I was visiting at WETA in 2014, because that will actually end up being quite related to what we will do in 3D printing. So one question to you: what is this? Anyone can guess? It's not a fingerprint, but it's pretty close. It's a finger knuckle. Okay, and what the reason I'm showing this thing is to really showcase just how much translucent our skin is. And of course, if you want to render skin realistically, you do have to take into account all of these intricate properties of the skin, including the reflection on the surface and the interaction of light with the various layers of the skin. And if you do this properly, only by doing this properly, you can really reproduce this very intricate visual properties of skin, such as these rims around the shadowed area, and so on and so forth. And this can be done by simply by realizing that our skin is actually a so-called participating medium that light can interact with just by bouncing around under the surface of the skin, and we can just use the process that is going to randomly follow a trajectory of a light particle under the skin. Unfortunately, if you do this in a naive way, much of the light tends to kind of like get lost and never actually make it to the surface, but that's unfortunate because that's where the light is actually going to come from. So what we would like to do here is to somehow inform the simulation that it should be actually going toward the light source, so that we can do what we are trying to do, which is establish some kind of a connection between the camera and the light source. And this was actually quite fun project to work on, because during this we have realized that there is a super tight connection to the simulations that are being done in Neutron Transport, and that have been done in Neutron Transport for the last maybe 60 or almost 70 years. And one specific problem that they are looking into in this Neutron Transport is the following. So you have your reactor core, and then of course you need to shield the core to ensure that none of the radiation that's inside of the core will actually make it outside. And somehow, like the standard would be that only 1 in the billion of the particles that are adjacent at the core of the reactor are allowed to actually make it out. So imagine that you are doing the simulation of the radiation in the slab just by following the particles, or following the trajectories of these individual particles. Well, this is going to take a lot of time because, of course, to get some reasonable statistical estimate, you need at least hundreds of thousands of these particles to make it through. So that would be a trillion particle trajectories that you would need to follow. And so that's of course that was of course completely impossible to compute 50 years ago on the computers, and it's still actually very difficult to compute even today. And that's why the researchers in nuclear engineering have been thinking about like how to change the simulation so that we can actually get more information about the particles that make it through, because we don't really care about any other particles. And so they modify the simulation such that when the particles are making a step forward, the step would be longer, and the steps of the particles in the way back into the reactors would be artificially made shorter. And by that, you can actually make sure that actually more of these particles make it through, and you have a better estimate. Now, how is this all related to skin rendering? Well, in fact, very closely, because like instead of having this shield, we have the layer of skin, and we're just, instead of trying to push the particles from one side to another, we're just trying to push them from the side through which they enter back to the same side. And it turns out that if you actually have some approximate solution of the lighting inside of such a slab, you can actually use this to inform the simulation to make the right decisions. And again, we've been amazed that 70 years ago or 50 years ago in this case, there's some mathematical result that actually described the solution very precisely, and we could just take it and apply it into this production renderer, and out came results essentially with less noise. Long story short, less noise. I don't have any like beautiful results because this was done, as a part of a visit at Weta, and of course it's very difficult to get any of the production results out of the company. So these are just some of our test renders that we did inside, and so this would be the simulation before, and this is the simulation that we got after this modification. And this there's been some follow-up work. And as I was following actually what other companies are doing, I have found out that over the years, exactly this kind of a simulation, which actually takes ideas from neutron transport and applies it to skin rendering, this is now used across the whole visual effects industry, and all of these companies are using it. So actually what I was talking about right here, this is something that you probably see on the screen anytime you watch a movie from at least any of these three visual studios. And now I will switch, with this I would switch to this 3D printing application. So we have been seeing 3D printing for quite a number of years now, so it almost sounds like an old news. But in fact it's not, because this technology is actually still very much developing, and especially when it comes to 3D printing detailed full color printouts, this is something that's been around only for the last few years. And this is exactly the printing technology that we are interested in. And indeed we can do quite amazing things, but when you start looking in detail at these 3D prints, as you can see here, well, they are still pretty far from what you would ideally like to be getting, right? So when you think about it, you could realize that in this 3D printing, in this realistic 3D printing, we might be somewhere where computer graphics was, back in 1995, where yes, we could do something, that looks quite okay on the screen, but we were still quite far away from the level of realism that we can achieve today. So you can actually think about this 3D printing problem as a generalization of what we do in realistic rendering, where instead of rendering for the screen, we are actually rendering for a full 3D printed object, something that you can take in your hand and play around with. So essentially the problem is that someone gives you a description of the appearance, something that you would want to 3D print, so that's the target appearance. Then our job as as technologists is to come up with this gears here, some kind of an optimization that tells the 3D printer what exactly it should be doing in order to get a 3D printout that looks as visually that has a close visual correspondence to the target. So that's what we're looking into here. And so we have had so far two papers on this topic, and I will just briefly go over both of them here. So we started in 2017 at SIGGRAPH Asia, where we were looking at texture reproduction. So these are some of the 3D prints that we produced then, and you can see that what we have are 3D prints with really highly complex and high frequency textures. So the enabling technologies to do this full color 3D printing is the so-called photopolymer jetting, which is really just your regular inkjet printer, except that the inks actually have some additives that make them sensitive to UV light, and so when you shine UV light on them, they will solidify. And so you just like inkjet your 3D printout layer by layer, and shine UV light on each of these layers and build the 3D print like that. And this is really the one and only technology today that can achieve full color textured 3D prints, where each of these droplets are just 20 microns. So really, you're getting some level of detail that's quite amazing. But there are some problems. One thing that is inherent to this 3D printing technology is the translucency of the printing materials, because they are sensitive to UV light. They harden by being exposed to UV light. So the UV light needs to be able to enter the material. So they just have to be translucent in the first place for this technology to work. So the manufacturer, they actually provide these CMYK printing materials, and they call them Vera opaque. And if there's one thing they all have in common, is that they are not opaque at all. They are actually incredibly translucent. And when you do just a regular 3D printing using such inks, what happens is that you're completely losing any detail in the textures that you would ideally like to reproduce on top of the 3D print. So this is one example, and you see, like, generally you get an okay reproduction, but any of the fine details are completely lost. And the reason for this is actually the multiple scattering of light that's happening inside of the volume of the 3D print that actually has for a consequence this bleeding of colors from the neighboring pixels of voxels. And of course, we would like to be able to produce with 3D print, essentially prototypes of just about anything, including very fine and sharp textures. And so this is what we set to do in the first place. So this is like a teaser of the results that we've been able to achieve. So we started just with these slabs, but of course we have gone further and generalized the solution to 3D, and this is something that will be presented tomorrow here at SIGGRAPH. So these would be the textures that we would like to reproduce. And this is what you see here. This is what would happen if you just send these textures into the 3D printer and let the default driver of the 3D printer do the job. Again, what you see here is an incredible loss of detail, and so the result really doesn't look good at all. And this is the kind of result that we were able to get with our 3D printer driver. So you see that, of course, we're far from being able to reproduce the input texture exactly, but the level of visual match is definitely much better than what was possible before. The motivation for this work partially actually came from this idea of image pre-correction. So when you think about it, when you think about this problem with 3D printing, it's that we have a texture that we would like to reproduce, and then it's actually 3D printed, and it goes through some kind of a degradation. This degradation is due to all of this light scattering inside of the 3D print, and it's inherent to the technology. So there's nothing we can do about this degradation. We know that the degradation will just always be there. And so the only thing that we can do is see if we can modify the input such that when it goes through this known degradation, it will actually come out the way we want it to look in the first place, right? And those are things that people actually have been doing in various kind of industries. This is actually very much used in displays, so you know the limitations of your display, so you would pre-correct the image before it goes into the display so that it comes out the way you want it. And there's been also work on using this to kind of like pre-correct your visual deficiencies that you may have. So of course, you know, when you are talking about visual deficiencies, the easiest solution is probably to correct the optical system by wearing glasses, but imagine that you can't do it, and then it becomes interesting. So this is the image that you would like the person to see, and if you show it to the person, then given the limitations of that person's eyes, this is what the person would actually see. So can you do better? Turns out that if you modify the input image so that it looks to a normal person, to a person with healthy eyes, it would look like this. Then if you show that image to the person with the deficiencies of the vision, he will see this thing. And that's a definitely much better match to the input image than what you see here, right? So this idea of pre-correction is actually something that works. And this is something that we can also use to fix the problem with the 3D printing. But of course, despite the fact that we're really interested in, so far, we are interested in just reproducing textures on top of the 3D prints, the problem is actually much more difficult for us because it's not really just image pre-correction. We have a full volume of full 3D stack of these 3D inks that we want to optimize. We want to figure out how the full volume should look like so that the texture looks the way it should. And so this is after good 2.5 years of not knowing what exactly we should be doing about it, we came up with a pipeline that looks as follows. So first, we have our target appearance. So this is what we would like to come out of the 3D printer at the end. Also, on the side, we have actually managed to measure all the scattering properties of the inks, so we know how exactly light will interact with all of these base inks that the material can use. So this information comes into this optimization step. Out comes a description of the volume that is then sent into the 3D printer, and out comes the 3D print. And now what happens here? What happens here is actually quite a classic approach where we essentially start off by guessing the solution, by guessing some kind of a distribution of the 3D prints, 3D inks in the full volume. And then we use rendering, we use light transport simulation to predict how the 3D print would look like should we use this distribution of materials. And then we see, yeah, well, the current solution doesn't really match what we want, so we modify the solution, get a new guess, again predict how it would look like, and just keep going until convergence. And so what's very important here is this step here, which is exactly the same light transport simulation that we're actually using to produce our nice, beautiful images. And it's exactly the same simulation that we used to render realistic skin. It's exactly the same thing because, okay, before we have the volume of the skin, now we have the volume of the 3D printing materials, but from the point of view of the simulation, it's exactly the same thing, just with slightly different parameters. So, as I said, the simulation of this visual prediction of the 3D printout, it really involves tracing many, many light paths under the surface of the 3D print. And by doing that, we are able to obtain a very, very good fit between the Monte Carlo rendering, that's the prediction, and the actual printout. So you barely can see actually any difference. And that's exactly what we want to have here, right? Because we really want to be able to know exactly how the 3D printout would look like should we print the current solution, so that we can be able to modify the solution in such a way that the match is actually achieved. Okay, so as I said, important step is this prediction. That's the rendering step, and then the solution refinement. We have some heuristics for this that I will not talk about here, and this is the process as it runs. So you start with some guess where we just take the texture and put it in the top layer of the 3D print, and we leave the whole volume of the 3D printout white. That's the first initial step. Of course, if you do this, because of all this translucency, the white light actually from the bottom will actually cause the visual texture on the surface to be very much desaturated. And so this is the initial result, and this is the initial configuration. So we see it's desaturated. We need to propagate. We need to actually saturate and increase the contrast of the materials in the 3D printout, and this is the next solution that we get, and then we can keep going like this until we get the final match. And eventually we send these results to the 3D printer to get this. So this would be the desired textures that we would like to obtain. This is the standard print that you get just out of the default printer driver. This is what you get using our color reproduction pipeline that I skipped over this because it wasn't like the most important thing. And this is what you get with just pre-correcting these textures and sending them through the default pipeline. So you see that this is still not working all that well. And this is our full solution. So our color reproduction pipeline plus our pre-correction that is used to ensure that that we obtain a sharp texture. So, long story short, this would be the state before, this is the state after. So you can see that we're getting a much better reproduction of these textures here. Of course, it seems a bit weird that we're talking about just flat texture in the world of 3D printing, but yeah, you have to just start somewhere. And of course, we went ahead and started extending this into 3D. In fact, the final result of the extension of this work to 3D is a full paper accepted to SIGGRAPH. It will be presented tomorrow at 9 a.m. in the session at 9 a.m. So I would like to invite you to come check it out. And just very briefly, the idea is again pretty much the same. So we have some kind of a description of the target appearance. We have some current solution. We look at the difference, and based on the difference, we just keep modifying the solution until convergence. And so in this case of this vase, this would be a cross-section of the vase that's showing the distribution of the materials inside of the vase. So white would be just a completely white material, and that you see that we have these CMYK inks distributed along the surface, and just by visual mixing of these materials, out comes the final target appearance. So some results of this. So just 2 example models that we have here. Again, GrabCAD, that's the default 3D printer driver. So you see that again, there's pretty much all the detail of the texture is lost. This is Cuttlefish. This is actually, let's say, a competing work coming from Fraunhofer Institute in Germany. But you see that even with this Cuttlefish driver, the results are pretty much lost. And this is again the results that's coming out of our pipeline. Another very interesting thing with this 3D printing is what happens when you start looking at very thin structures. So, for example, just it's a bit of a contrived example, but it actually shows it very nicely. So imagine that you have this slab that is just 0.5 millimeter thick, and you would like to have this texture on one side of the slab and this texture on the other side of the slab. Okay, so that would be your target. And this is what happens if you just take a 3D model textured in this way and send it to the default printer. So essentially, because of this translucency, you know, the texture from one side will completely creep to the other side, and you will totally lose the notion of what you should be seeing on this side in the first place, right? I remind you, this is what we would like to be seeing here, and this is what actually comes out as we print it out. So just sending this input through our pipeline without any further considerations already produces results that are quite a bit better. You start seeing the right images on the two sides, so that's great. But we have also introduced actually a new gamut mapping where we take the input textures and we look at the local geometry of the 3D printout, and we say, okay, given the local 3D geometry, what is the best that we can do in terms of reproducing the individual colors? And by doing that, you get a result which is quite a bit further in terms of quality than what we could do before. So of course, you know, the window from one side still creeps a little bit in the image that you see on the other side, but generally the result is very much improved. Of course, it doesn't work only for slabs, so we can apply it to any 3D geometry. And so one example that is geometrically very complicated, and this is why we took it as a test, is this thing that we call the Octostar. So this is the input 3D geometry. And this is what comes out of the default 3D printing driver, and you see that, you know, the input actually should be red from one side and white from the other side. And of course, if you send it in, you know, all of this red color will kind of like bleed through, and you will not be seeing the white as you should. And again, if you send it to our algorithm, you get a much more faithful reproduction of the input, of course within the limits of what is physically possible using this technology. And so you might be asking, why is this important at all in the first place? And so I have this interesting collaboration with a student from Brno University of Technology in the Czech Republic, where this was a person who he lost his eye when he was young. And he's kind of like, he's never been quite satisfied with the prosthetics that he was given actually over the years. And this is still today is actually done really by hand processing, okay? So either glass or acrylic, but this is really done by a person, you know, sitting in front of the patient and painting the eye after the healthy eye. And so he said, like, can we do better? And so he scanned and remodeled his healthy eye, and he got some initial result, which is shown here. And then we got together with him, and we said, okay, well, we see actually the exact same problems that we were seeing in the original printout. See that there's a lot of blur that shouldn't be there. So can we actually, by applying our algorithms, can we do better? And indeed, these are really very, very initial results. So this is by far not what we should be really getting. But already what we can see here is a much increased sharpness, and we were able to get a much better reproduction of the healthy eye, of the appearance of the healthy eye. So this is just one example of the potential application where you can actually use this technology. And I'm pretty sure that there are many more. So the take-home message that I really wanted to show here is that there's this very powerful idea of light transport simulation. It draws some ideas also from other fields such as neutron transport, nuclear engineering. And so far we've been using it mostly to create all of these beautiful images for various applications such as visual effects, or architectural visualization, but most of this was always meant to go on the screen. And so the message that I wanted to show here is that, well, this is not it, okay? The same ideas, the same simulations can actually be used to make progress in other fields than just images on the screen, and one of them is the 3D printing that I was showing here. So of course, this is still super slow, but we are already working on ways of making it faster. And we have plenty of other ideas to improve this, to increase the gamut of what could be 3D printed, and so on and so forth. So this is it for the actual content of the talk that I had here. I would just like now to go back to this idea of the new lab, Chaos Research, that I mentioned at the beginning. And I would just like to say what we're planning to do here. So it's a research lab which is established between Chaos Group and Charles University in Prague. And within this group, we're looking at open-ended research, some questions that we need to get answered within 2 to 5 years, let's say. And so one thing is rendering. Of course, rendering is not done, and there's plenty of work to be done there. So this is where we come from, and this is what we will keep doing further down the road. But there's two other directions which we would like to work on, and I would just mention them very quickly. So one thing is assets. So automatic generation of assets, and second thing is some computational support for individual artistic expression. And so we have been seeing all these images generated by neural networks, and if you go to this web page, this person does not exist, and you keep reloading the page a couple of times, you will get some really intriguing and realistic images of human faces, of humans that have never walked the planet Earth. And of course, when you look at it, you realize very quickly that, well, if we can generate the faces, we could probably generate any other classes of images. And one, for 3D printing, for 3D artists, getting access to high quality assets has always been an issue. And you would have to go to some library, pay $15 to buy a nice HDR Sky. Well, can we probably do better? And turns out, yes, we can definitely generate plenty of HDR Skies today, and that's already something that we are working on. And so these are our initial results. And of course, if this pans out, if this works out well, we of course want to generalize this idea to all of the other possible assets that one needs to create realistic 3D scenes. And another aspect that I wanted to mention a little bit is this individual artistic expression. So of course, 3D artists within the realm of 3D art, when you are an insider, you can spot the differences between a style of a person doing this visualization as opposed to a person doing another 3D visualization. But for an outsider, these images really look all the same. And so the idea is that can we do better? Can we somehow support, go back to supporting individual artistic expression in architecture? And this is also another direction of work that we're trying to do here. So this is an example of a sketch drawn by an architect. And of course, in the process of creating architecture, there's always lots of modifications, lots of tweaking. And so, having to redraw this thing every single time you move the door a little bit by 20 centimeters, or you try another version, that is probably not very efficient. So the first thing that we started looking into was, okay, if we show the computer an image like this, can we then, just by analyzing this, can we then automatically regenerate different views and different variations of the same building? And this is something that's almost already working, and once we get it working, we will take it further down. So with that, I would like to wrap up. I would like to invite you, anytime you're in Europe and you want to stop by in the beautiful city of Prague, make sure to stop by also at our university, which is really in the heart of the tourist area of the city. This is where the company is, very much central. So do come and say hi and stay to work with us. We're looking for people, of course. And with that, I would like to thank all the students and collaborators that helped with this work, and especially Oscar and Tobias for some of the slides. Also funding and of course you for coming here. Thank you.